Understanding nuclear power. When we hear the term nuclear energy, it often evokes a mix of fascination and caution. Some people imagine vast power stations quietly generating electricity. Others think of glowing fuel rods or the mushroom clouds of history. Yet behind the word nuclear lies a story of remarkable engineering and physics, one that transforms the tiny forces inside atoms into steady, reliable power for entire nations. To understand how a nuclear power plant works, we need to start from the smallest building blocks of matter, atoms. At the heart of each atom is a nucleus, composed of protons and neutrons, bound together by incredibly strong forces. In certain heavy elements, like uranium, that nucleus is unstable. It can split apart, releasing energy, a process known as nuclear fission. This energy, when controlled, becomes one of the most powerful and efficient sources of electricity known to humanity. The basics of nuclear fission. Nuclear fission happens when the nucleus of an atom divides into two smaller nuclei, releasing a large amount of energy in the process. When uranium-235, one of the isotopes commonly used in reactors, absorbs a neutron, it becomes unstable and splits almost instantly. This split releases two key things: energy and more neutrons. The released energy appears primarily as heat, the same kind of heat that can boil water. The neutrons, meanwhile, can go on to strike other uranium nuclei, causing them to split as well. This sets off a chain reaction. In a nuclear reactor, this chain reaction is carefully managed to ensure it remains steady. Not too fast, not too slow. If too many neutrons are absorbed, the reaction slows down. If too many escape control, it can accelerate. The art of nuclear engineering lies in maintaining this delicate balance so that energy is released smoothly and predictably. Inside the reactor core, at the heart of a nuclear power plant is the reactor core, where the fission reactions take place. Inside the core are thousands of fuel rods, long metal tubes filled with small pellets of uranium dioxide. Each pellet, about the size of a fingertip, contains enough energy potential to power a household for years. When the reactor is operating, neutrons collide with the uranium atoms inside these pellets, causing fission and releasing heat. To control the reaction, engineers insert control rods made of materials like boron or cadmium that absorb neutrons. By adjusting how deep these control rods are inserted into the core, operators can regulate the rate of fission, much like pressing the accelerator or brake in a car. The core is immersed in a coolant, typically water, which serves two vital purposes. It transfers the heat away from the fuel rods and also slows down the neutrons, so they are more likely to cause additional fissions. This slowing process is called moderation, and it's essential for maintaining a stable chain reaction, turning heat into electricity. The heat generated by fission doesn't directly produce electricity. Instead, it's used to create steam, which drives a turbine connected to a generator, the same basic principle that underlies coal, gas, or geothermal power plants. In a pressurized water reactor, PWR, the most common type in the world, water flows through the reactor core under high pressure so it doesn't boil. This hot, pressurized water then passes through a heat exchanger, or steam generator, where it transfers its heat to a secondary loop of water. This second loop boils and produces steam that spins the turbine blades. The turbine is connected to a generator, which converts the mechanical rotation into electrical energy through electromagnetic induction. The electricity then travels through transformers and transmission lines to homes, businesses, and industries. After the steam passes through the turbine, it's cooled and condensed back into water using a condenser, often linked to large cooling towers. The cooled water is pumped back to repeat the cycle, ensuring minimal waste and continuous operation. Safety systems and redundancy. Nuclear power plants are designed with multiple layers of safety systems, Every critical function has backups, and many of those backups have backups of their own. The guiding philosophy is defense in depth. No single failure should ever lead to danger. The first line of defense is the fuel pellet itself. The uranium dioxide is a ceramic material that holds most fission products within its structure. The second line is the metal cladding, usually made of zirconium alloy, that seals the fuel pellets and prevents radioactive gases from escaping. Surrounding the fuel rods is the reactor vessel, a thick steel container that can withstand immense pressure and heat. Around that vessel is the containment building, a massive structure made of reinforced concrete and steel, designed to prevent any release of radiation into the environment, even under extreme conditions. Cooling systems also have redundancy. If one system fails, others automatically start. In modern reactors, passive safety systems rely on gravity, natural circulation, and physical laws, not human intervention or electricity, to ensure cooling continues even in emergencies. The fuel cycle and efficiency. The nuclear fuel cycle begins with mining and refining uranium. The uranium ore is processed to extract uranium-235, the isotope capable of sustaining fission. This uranium is then fabricated into fuel pellets and loaded into reactor assemblies. Over time, as the reactor operates, the concentration of uranium-235 decreases, and new elements like plutonium are created through neutron absorption. Eventually, the fuel is no longer efficient enough to sustain the reaction and is removed. This is called spent fuel. But spent doesn't mean useless. About 95% of its content is still energy-rich material that can be reprocessed and reused. Many countries have programs to recycle nuclear fuel, reducing waste and extending resources. Even without reprocessing, the volume of waste produced by nuclear power is small compared to fossil fuels. A single person's lifetime electricity use from nuclear power would create roughly the size of a soda can in high-level waste, all of which is safely contained and managed. Comparing emissions. Why nuclear is low carbon. One of the strongest arguments for nuclear energy is its exceptionally low carbon footprint. During operation, a nuclear power plant emits no carbon dioxide. The entire process, from mining uranium to decommissioning, results in life cycle emissions comparable to those of wind and lower than solar when energy storage is included. In contrast, fossil fuel plants burn hydrocarbons, releasing vast amounts of CO2 directly into the atmosphere. Even clean coal or natural gas plants produce hundreds of grams of CO2 per kilowatt hour. Nuclear power, on average, produces less than 15 grams, a fraction of that amount. This matters deeply in the fight against climate change. While renewable energy sources are expanding rapidly, their intermittent nature makes them dependent on stable, dispatchable sources that can produce power when the sun isn't shining or the wind isn't blowing. Nuclear energy fits that role perfectly: clean, consistent, and independent of weather. Addressing safety myths. Public perception of nuclear power is often colored by the few major accidents that have occurred, most notably Chernobyl in 1986 and Fukushima in 2011. These events are tragic and instructive, but they represent extreme outliers in a long history of safe operation. Modern reactors are designed with entirely different safety principles. Chernobyl lacked a proper containment structure and used an unstable reactor design that could not shut down safely under certain conditions. Fukushima, while damaged by an unprecedented natural disaster, has since led to global safety reforms that ensure even better protection against loss of power and cooling. Statistically, nuclear energy remains one of the safest forms of electricity generation when measured by fatalities per terawatt-hour, safer even than wind and solar when manufacturing and mining accidents are included. Radiation exposure from living near a nuclear power plant is minuscule. often lower than what one receives from natural background radiation, or even from eating a banana, which contains naturally radioactive potassium. The reality is that nuclear energy operates under some of the strictest safety regulations of any industry, and its record shows that those measures work. Waste management, the real picture. Nuclear waste often dominates public debate, but the facts tell a more reassuring story. All the high-level waste produced globally, over 70 years of nuclear power, could fit in a single football field, stacked just a few meters high. Unlike the billions of tons of carbon dioxide from fossil fuels, nuclear waste is contained, tracked, and managed. Spent fuel is stored first in cooling pools, then in dry casks. Robust containers made of steel and concrete that safely isolate the material for decades. Many countries are developing deep geological repositories, where waste can be safely stored thousands of feet underground in stable rock formations. The scientific consensus is that this method provides long-term safety far beyond the timescales of any human activity. And as technology advances, future reactors, especially those of the next generation, will be able to consume existing waste as fuel, reducing both its volume and its radioactivity. Modern reactor designs and future innovations. The reactors built today are not the same as those of the 1970s. The new generation of designs, known as Generation 3D Plus and Generation 4 reactors, incorporate advanced safety features, higher efficiency, and better fuel utilization. Some new designs are small modular reactors, SMRs, compact units that can be built in factories and shipped to sites. These reactors are designed to shut down safely without any human input, using passive cooling systems. SMRs can be deployed in remote areas, replace aging coal plants, or supplement renewable energy sources. Other innovative concepts, like molten salt reactors or fast neutron reactors, promise to recycle spent fuel, produce less waste, and operate at higher efficiencies. The field of nuclear fusion, the process that powers the sun, is also advancing rapidly, offering the prospect of nearly limitless clean energy in the future. But until fusion becomes practical, fission remains our most reliable, large-scale, low-carbon option. Nuclear power and grid stability. Electricity grids need balance. Supply must always match demand. Renewable sources like solar and wind are variable. Their output depends on weather and time of day. When clouds cover the sky or the wind dies down, generation drops. To keep lights on, other power sources must fill the gap. Historically, fossil fuels have played that stabilizing role, but they come with high emissions. Nuclear plants, on the other hand, provide baseload power, continuous steady output that keeps the grid stable day and night. Moreover, modern reactors can load follow, meaning they can adjust their output in response to changing demand. This makes nuclear energy not only a source of consistent power, but also a flexible partner for renewables. As nations move toward decarbonization, integrating nuclear power ensures that clean energy is available 24/7. Without it, grids would rely more heavily on fossil fuels for backup, undermining climate goals. Economic and environmental synergy. Building a nuclear plant requires significant upfront investment, but once operational, the costs of fuel and maintenance are relatively low. Over a lifespan of 60 years or more, nuclear plants provide stable electricity prices and protect consumers from volatile fossil fuel markets. Environmentally, nuclear power preserves landscapes. A single plant can produce gigawatts of electricity, using only a few square kilometers of land, compared to the vast areas required for equivalent solar or wind farms. It also avoids the air pollutants, sulfur dioxide, nitrogen oxides, particulates, that harm human health and ecosystems. In this sense, nuclear energy offers a unique combination of density, durability, and cleanliness that few other energy sources can match. The human element, operation and training. Behind every reactor is a team of highly trained professionals, engineers, technicians, and operators who monitor and maintain the plant around the clock. The level of precision and discipline required in nuclear operations is extraordinary. Every procedure is reviewed, every system tested, every anomaly investigated. Workers undergo continuous training, including simulations of emergency scenarios. This culture of safety and accountability is what makes nuclear energy not just technologically advanced, but humanly responsible. The people who run these facilities understand deeply the trust placed in them, the trust to generate power safely, to protect the public, and to contribute to a cleaner future. Common misconceptions. It's easy to misunderstand nuclear energy because it deals with invisible forces and complex technology. Some fear that plants can explode like bombs, which is physically impossible. Nuclear reactors operate at low enrichment levels and cannot produce the rapid chain reaction needed for a weapon. Others believe that radiation from nuclear plants harms communities, yet environmental monitoring consistently shows emissions far below natural background levels. Finally, some think that renewable energy alone can replace all fossil fuels, but practical experience shows that without nuclear power, maintaining reliability becomes difficult and expensive. Energy systems need diversity, and nuclear provides that backbone. Lessons from the past, vision for the future. The history of nuclear power is filled with lessons. Mistakes have been studied in depth, leading to new standards, stronger designs, and a better understanding of risk. Each generation of reactors is safer and more efficient than the last. At the same time, society's energy demands are growing. As billions seek access to clean, affordable electricity, the world must expand its energy systems without worsening climate change. Nuclear energy provides a proven path toward that balance: high output, low emissions, and long-term sustainability. Countries that invest in nuclear today are not turning back to the past. They're building an energy future capable of supporting electric vehicles, green hydrogen production, and resilient infrastructure. Why nuclear energy matters? Nuclear power is not a silver bullet, but it's an essential tool in our arsenal against climate change. It complements renewables, replaces fossil fuels, and offers a way to produce massive amounts of electricity without choking the planet with carbon. It is also an expression of human ingenuity, our ability to harness the forces of nature responsibly, to turn the invisible energy of atoms into light, heat, and progress. In a world that demands both clean energy and reliability, nuclear power stands as one of the few solutions that can deliver both. The promise of controlled fire. From the splitting of a single atom comes a profound lesson. Power is not just about energy, but about control, understanding, and purpose. Nuclear fission, when managed with care and wisdom, offers humanity a source of light that burns without smoke, a fire of the mind as much as of the atom. As we move into a century defined by climate challenges and technological innovation, nuclear power remains a quiet, steadfast ally. It is low in emissions, proven in safety, and capable of stabilizing our grids when other sources fall silent. In the end, nuclear energy reminds us that the solutions to our greatest challenges often lie not in fear, but in knowledge, and in the courage to use that knowledge for the common good.